The structure of the Earth is not easy to discover, because even with all the technology we have available to us, the deepest hole ever drilled into the Earth is only 12 kilometres deep, and the distance to the centre of the Earth is over 6,300 kilometres. Scientists have had to use methods other than direct observation to work out the structure of the Earth. The rocky surface layer of the Earth is called the crust. It varies in depth, but its average thickness is about 30 kilometres. The continents of the Earth rise above the oceans where the crust is thicker, and the oceans fill the thinner regions of the crust, but the crust is thicker than the deepest ocean. Underneath the crust is a layer of the Earth called the mantle. This is very thick, about 3,000 kilometres, and is so hot that the rock is more like a very thick liquid than a solid, and can flow very slowly. Below the mantle is the core, comprising the outer core and inner core. These are both even hotter, about the same temperature as the surface of the Sun. The outer core is made of liquid iron, and the pressure in the inner core is so high that the iron and nickel found here are solid. Experiments to estimate the age of the Earth place it at about 4,500 million years old, give or take 50 million years, although the universe is dated at nearly 14,000 million years old. The simplest kind of life on Earth have been around for about 3/4 of the Earth's history, although what we might recognise as being living organisms have only been around for the last 500 million years, and from the Stone Age to the present day is only a period of around 2 million years. There are several different ways that scientists have used to work out the Earth's structure. Wherever earthquakes happen, shock waves travel through the Earth. These are measured by a network of sensors all over the Earth's surface. The time taken for the shock waves to travel and their size gives the information needed to build up a model of what the different layers of the Earth are made from and their thickness. Further evidence comes from working out the mass of the Earth. By observing how the Earth moves in its orbit around the Sun and how the Moon moves around the Earth, scientists have worked out what the Earth's mass must be. The substance which best matches the size and mass of the Earth is iron, which also happens to be the most abundant metal in the universe. Scientists weren't too surprised that the centre of the Earth was hot. After all, it was formed from a ball of molten rock, and it would be expected to be still cooling down. Scientists were surprised to find that the Earth's core was hotter than it should be, given how old it is and how much it should have cooled down. In the core of the Earth, there are natural radioactive processes taking place which release heat energy, slowing down the rate of cooling and keeping the core hot. The Earth's crust is not a single solid sphere like an eggshell, but the crust and upper part of the mantle are cracked into a number of large pieces. These float on the thick liquid layer of the mantle and can move slowly around. We call these pieces tectonic plates and have measured their movement at a few centimetres per year. You may not realise that Stanford and New York are getting further apart, but over your lifetime the distance will increase by a couple of metres. The process is called continental drift.
The Earth's surface is broken up into 7 major chunks called plates. They're so enormous that they can carry an entire continent and extend far under the sea. Strip away the Atlantic Ocean and you can see a long boundary between 2 of these plates that runs along the ocean floor until it rises above the waves, cuts through Iceland to eventually join up with the rock face at Thingvellir. It's possible to see this plate boundary from a completely different perspective. This is a very cold place to go scuba diving. The water's just 4 degrees Celsius. But it's worth it. Because I'm actually swimming in the gap between the 2 giant plates that run through Iceland. To my left, the North American plate, and to my right, Europe. These sheer rock faces were once joined together, but driven by immense geological forces, the land was split apart to create these deep chasms which filled with water. It's hard to imagine a force that can move continents apart. Yet this is precisely what the Earth's inner heat is able to do. It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in 2 directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. The continents here are drifting apart at 2 centimetres every year. In my lifetime, we're talking just a couple of steps. Even in 1,000 years, that's just 20 metres. It's only when you start to think in terms of millions of years that you realise just what can happen.
Continental drift has been going on throughout the Earth's history. England was once in a hot tropical location on the Earth's surface, which is shown by fossils in English rocks of creatures which only lived in tropical climates. Watch this animation of how the movement of tectonic plates has rearranged the continents of the Earth in the past 300 million years, forming, then breaking apart huge supercontinents to position them where they are today. See when you first can recognise the landmasses that will become Europe and England. The model of continental drift has been projected forward in time as well, showing how the continents are predicted to move in the future. Watch where England goes and how a new supercontinent is formed. The idea of countries moving around is not one the early scientists were willing to accept easily. Everyday experience suggested that the Earth was solid and countries were fixed in place. Until we were able to measure the movement of countries towards or away from each other accurately using satellites, one of the key questions had been what could possibly be powerful enough to move a continent. The intense heat in the core of the Earth makes the liquid close to the core less dense, so it rises slowly towards the crust. The cooler liquid near the Earth's crust is more dense and sinks towards the core, setting up flow patterns called convection currents in the mantle. Remember that the tectonic plates float on the liquid of the mantle, and so they're driven along by these convection currents. The movement of tectonic plates may be slow, but because the plates are so massive, the effects at their edges are spectacular. When tectonic plates push into one another, one plate is forced up while the other is forced underneath. Volcanic activity is common at such plate boundaries, and mountain ranges such as the Andes were formed in this way. Deep ocean trenches can form where plates are moving apart. When plates move past each other, the grinding together, sticking and slipping of one plate against the other is what causes earthquakes.
In the early morning of January the 17th, 1995, instruments in a lab in western Japan picked up a burst of intense electromagnetic radiation. It was the signature of a massive earthquake which had just struck the city of Kobe from its epicenter 20 kilometers to the southwest. There was no warning. 180,000 buildings were destroyed. An urban area 20 kilometers long and 4 kilometers wide was totally wrecked. Nothing moved in or out of Kobe by road or by rail for 3 days. The root of the disaster was a shock that happened on the boundary between the Eurasian and the Philippine plate, a boundary that runs right beneath the city. There is a direct relationship between plate margins and earthquakes throughout the world.
Scientists know that volcanic eruptions and earthquakes are most likely to happen where the plates meet, and they can predict when the forces are building up to the point where an earthquake or eruption is likely. Of course, there's no way of getting measuring instruments deep enough into the ground to be able to measure the conditions there, so when an earthquake or volcanic eruption will actually happen remains impossible to predict. The final video clip illustrates the natural beauty and incredible power of volcanoes.